My name is John Polimeni, and I'm going to present a quick summary of our recent MRM article published in February 2016 entitled Reducing Sensitivity Losses Due to Respiration and Motion in Accelerated Echoplanar Imaging by Reordering the Autocalibration Data Acquisition. The motivation for this work was our observation of the effects of segmented multishot EPI autocalibration, or ACS data, for accelerated EPI reconstruction on time series SNR. Here's an example of time series SNR map acquired from R=3 accelerated EPI data, reconstructing using grappa using conventional multishot EPI as ACS data. We noticed a conspicuous discontinuity of TSNR across slices when using segmented EPI as ACS. This discontinuity could be removed if we reconstructed the same data with single-shot EPI ACS, which has its own problems that I'll talk about in a few slides, but this tells us that segmented EPI ACS causes non-uniform TSNR, which constitutes a detection bias for studies using EPI such as functional diffusion or perfusion MRI. I want to point out that this discontinuity is really caused by temporal instability and is not caused by intensity differences across slices. If we look at the images themselves, we see smooth intensities across slices, so the discontinuity is unlikely to be caused by something like slice crosstalk. We do see discontinuity, however, both in the temporal standard deviation and temporal SNR maps, demonstrating that this is an effect driven by varying levels of temporal instability across slices. So the question is, why might there be a temporal instability in the grappa reconstruction across slices when using segmented EPI as ACS? Well, we know that multishot EPI is vulnerable to subject motion and dynamic B0 changes such as those driven by respiration. So the solution we came up with was, to remove this vulnerability, was to simply reorder the acquisition of segments in multishot EPI to minimize the time interval between segments within each slice. So to review, in conventional multishot EPI, we start by acquiring segment A of slice 1, followed by segment A in slice 2, segment A in slice 3, and so on. Then 1 TR later, we return to slice 1, and acquire segment B in slice 1, then segment B in slice 2, and so on. What this means is that we have adequate T1 recovery between segments, but the long time interval between all segments acquired in a slice causes this vulnerability to motion. A solution is to simply reorder the acquisition of these segments, so instead we start with segment A of slice 1, then we acquire segment B of slice 1, and segment C of slice 1. Then once slice 1 is finished, we move on to slice 2, and so on. While this reordering causes a minimal time interval between segments, so there's less T1 recovery, this acquisition is much more robust to motion and dynamic phase changes. This reordered segmented EPI is known as FLEET, or Fast Low-Angle Excitation Echoplanar Technique, originally introduced in MRM by Sir Peter Mansfield. There are two variants, one in which we vary the excitation flip angle so that each segment has equal magnetization, or if there are multiple T1s present, we can simply use the same low flip angle for all segments. Here's an example, TSNR maps using different ACS acquisitions. For the conventional segmented EPI, we see that this discontinuous TSNR is across slices. When we use FLEET for ACS and reconstruct the same data, the discontinuous TSNR is removed and the overall TSNR is increased. We also see that FLASH or GRE-based ACS method can also remove this discontinuous TSNR across slices. Here's a summary of the TSNR achieved by multiple ACS acquisitions. We see that the FLEET ACS method provides a nearly 20% improvement in TSNR compared to the conventional multishot EPI ACS. This means that simply by reordering the acquisition of the segments and using the exact same reconstruction, we can achieve a sizable boost in TSNR. So here's a comparison of the performance of various ACS methods in the presence of B0 inhomogeneity. Unlike single-shot ACS or flash ACS, the FLEET ACS is distortion matched to the accelerated EPI data, therefore produces the lowest ghosting levels in the presence of B0 inhomogeneity. So to demonstrate the effects of motion during ACS acquisition, we constructed an anthropomorphic head phantom and rocked it during the ACS acquisition. When using conventional multishot EPI ACS, we see strong aliasing artifacts in the image reconstructions. However, when we use a FLEET ACS acquisition and reconstruct the same data, the aliasing artifact is removed, showing this motion insensitivity of FLEET ACS. So in order to understand the source of discontinuous TSNR across slices, we performed an experiment in which we first asked subjects to free breathe during the ACS acquisition, and when using conventional multishot ACS, we again see strong TSNR discontinuity across slices. However, when we asked subjects to perform a breath hold during the conventional multishot EPI ACS, we saw that this discontinuous TSNR across slices was removed. In either case, we saw smooth TSNR across slices when using FLEET ACS. What this means is that if we want to remove this discontinuous TSNR across slices, one can either ask subjects to perform a breath hold during the conventional multishot EPI ACS or use FLEET. And just to demonstrate again that this is related to temporal stability, we see here that the discontinuous temporal standard deviation seen across slices when using conventional multi-shot EPI ACS can be removed by a breath hold. So this again tells us that Fleet helps to prevent phase errors between shots that are caused by dynamic B0 changes. So to summarize the benefits of Fleet ACS, we've seen that it removes the SNR discontinuity across slices, which was shown to be caused by respiration. It provides motion robustness by reordering the motion vulnerable multi-shot EPI. It increases the TSNR relative to multi-shot EPI ACS and flash ACS. Importantly, it shows us that auto-calibration is possible using EPI data despite the intrinsic Nyquist ghosting or static phase errors in EPI ACS data. Finally, we saw that it reduces aliasing or ghosting in the presence of B0 inhomogeneity because Fleet ACS is echospacing matched and therefore distortion matched to the accelerated EPI data and therefore more compatible. So with that, thanks for your attention, and I hope that you check out our article.